pseudorandom permutations. And yeah, thanks. Just hand it over to Ryan.
Okay, this is going to be about several papers by this guy William, who's over here, and also the two people sitting next to him will make an appearance in this paper as well. Okay, I used to read blogs back when they existed, and this feels no less. Tim Gowers had a blog, and one time in 2013 he posted like several articles with these like provocative titles about P and NP, and I'll just read you a little clip from one of them. It's like a really long blog post. He's talking about like this. He's like talking about, let's define a 3-bit scrambler to be like something, and then he's talking about composing a lot of these into a circuit by picking a random sequence of 3-bit scramblers and putting them together. So I'll just tell you what he was talking about in my own language. This is a picture of like maybe a composition of 3-bit scramblers, or as I would call it, a classical reversible circuit. Yeah, classical refers to not quantum actually, but let's just call it not a reversible circuit. So the picture here is it's a kind of like circuit from like basic complexity that implements a permutation on n-bit strings. How does it work? You have like n like wires, those are the horizontal lines, and each one of these blobs is a gate, and in this picture each gate takes in 3 bits and outputs 3 bits, and each gate implements one of the 8 factorial possible permutations on 3-bit strings. Okay, so this thing G1 might be implementing this little permutation on 3-bit strings, and this G2 might be implementing this little permutation on 3-bit strings, and so forth. And then if you put them all together, it naturally implements a permutation on n-bit strings in like the natural way. Like if a string comes in, you know, you pass it through the first gate, and it's going to change to 0, 1, 0 to like whatever that goes to. I can't see, but apparently 1, 0, 0. And then you keep going, and it'll pass the 1, 1, 1 through this gate, and that'll change to something else. And then you pass it through all the gates, and at the end it comes out, and you have another n-bit string. Okay. You might ask, is it possible to compute every permutation on n-bit strings just using these circuits that have like these little local gates that operate on 3 bits? And the answer is yes. Actually, strictly speaking, no. It's only the even permutations, but never mind. The answer is yes. This was proven by John Coppersmith and Edna Grossman back in 1975, and they were motivated by cryptography. That's why we're also all here. Also, just like in the usual like circuit, like Boolean circuits, you know, most permutations need exponentially many gates. Actually, this was studied even earlier by people like Landauer and Bennett, whose motivation was physics, and physics will make a small return towards the end of this talk as well. Okay, I guess in cryptography terms, I'm not into cryptography, so you all know more than me about this, but I guess it's sometimes called a block cipher of size n. And it's kind of like the key is the circuit itself, like where the gates are and which of the 8 factorial permutations they're doing. So if you were to describe that in bits, if there are like S gates, that's the size of the circuit, then for each gate you have to say what little permutation it's doing. That's constantly many bits, and also which 3 wires it's on. That's like 3 log n bits. So the key size is it's basically S times log n. Yeah. Oh, great question. I didn't say why 3 bits. It turns out that if you only do 2-bit permutations, then this theorem is not true. You can only get a very small subset of all possible permutations. I guess because every 2-bit permutation is like the output bits are affine functions of the input bits. You just consider all the possibilities. So 3 is the smallest for which you get universal reversible circuit. And another feature about this is like, yeah, I mean, this is manifestly invertible. It computes a manifestly invertible bijective function because you compute the inverse function just by running the circuit backwards. I mean, you just make these the inputs and these the outputs. And each little gate you have to like reverse the arrows inside the gate. You have to compute the inverse permutation. So I guess, I mean, don't laugh. This is maybe the naivest way you could use this to do something cryptographic. I guess it's too simple to be how you actually do it. But you know, if Alice and Bob wanted to do private key encryption and they both like have this secret circuit in their mind, then you could try to like do encryption of an n-bit message with Alice just running the message through the circuit. And then and that will look random to potentially outside observers. And Bob can decrypt by just running the message that he gets through the circuit backwards.
So imagine if you had to consider two global permutations of 0, 1 to the n. So you add one modulus to the n and shift by 1. And then the key determines the random scheduling of compositions of such permutations, which can also be plausibly conjectured to be pseudorandom. How would that compare to this more local approach, or is there any relation to it?
Yeah, they would be different. I mean, I guess the point is there's many ways you could imagine trying to make, well, these block ciphers, and even ones that are like sort of manifestly invertible. This version with just like really local gates is like one particularly simple way to try to fit.
What is the very? So take some fix, I don't know, two or more. I believe this was an old proposal of global permutations from 0, 1 to the n. Again, very simple ones, like add one modulus to the n and shift by 1. And now the key to compose polynomially many, secret composition of polynomially many of these constant families.
Yeah, we'll see some things that are similar to this as the slides go on. Yeah, so I mean, is this good? Is this like cryptographically secure? So actually, Gowers, I mean, wrote about this in his original paper from 1996, and it's kind of also thought about in these are both the PhD theses of Richard Cleve and Oded Goldberg. Thought about exactly this, and he's like, okay, let's pick some constant C. Like he's like, I don't know, how about 5? And just said, let's make a uniformly random reversible circuit with n to the 5 gates. Just like throw it on n to the 5 gates, each one choose the 3 incoming wires at random. Choose from the 8 factorial permutations at random. That gives you a random permutation with like very small circuit complexity. But perhaps it's cryptographically secure, like it's a PRP family. So maybe you want to see it slightly more precisely. This family of permutations you get with a key size of like n to the c log n. We pick a random reversible circuit with n to the c gates. Maybe it has this property that any polyton adversary A that gets oracle access to a permutation on n-pit strings can't tell the difference if it's getting oracle access to a truly random permutation or like one of these pi k's that has very low circuit complexity. And what a great conjecture! Yeah, perhaps it's true. It's such a nice way to like try to make a pseudorandom permutation family. So why might you think it's true, or why might you be motivated to hold it true? Well, things like DES and AES, which I'm not an expert. There's better experts here. But they kind of look like this. So particular families of like n-bit reversible circuits with some kind of like gates in them. Maybe the gates are like more complicated than these local gates, like you were saying. I don't know if this is right, but I was just trying to copy off Wikipedia. But I think like AES has 128 bits and 14 rounds, or where each round you do some kind of relatively simple operation on a subset of bits. Okay, so maybe these are a bit different in the sense that you're really having all your operations on like the smallest number. Moreover, why you might be interested? Well, I mean, you might hope, in fact, for security of like not just Gowers' conjecture, but like maybe even with like some practically motivated further restrictions. Like you can even try to make the gates a little bit simpler. Like you can have these kinds of gates where you don't put like any old 3-bit permutation, but like these special ones that come up in cryptography and quantum where like the first 2 bits stay the same and the 3rd bit just gets toggled based on some function of the first 2 bits. And if you're gonna, I don't know, put this in a chip or something, you might hope for like some even simple gate architecture, which I'll draw pictures of in a second, where you have like 1D or 2D local architecture for the operation, which I think occurs in AES as well. So one simplification, for example, of the architecture is to have you might call 1D local gates, where the gates have to operate on like 3 consecutive wires. Okay, it's both easier to draw on the slides and presumably easier to implement in hardware. That's maybe a further simplification you could hope for. So a big-ish like picture of a 1D local reversible circuit might look like this. you could even hope to simplify this picture somewhat further. There's a pretty good kind of architecture called 1D brickwork architecture, where basically you just put like, down like a row of like basically n over 3 gates. And you just have layers of these n over 3 gates. And you have to like stagger it slightly, so you're not literally, dividing the wires into groups of 3 that never talk to each other. But if you do this, it's called brickwork architecture. And this is actually kind of cool if circuits like this could even be cryptographically pseudorandom, because the architecture is totally fixed. The only thing that's like not specified is which of the 8 factorial or 16 different gate identities you put in here.
Okay, so can't you do general routing?
Is that
No, in that sense, this is universal architecture with some overhead.
Yeah, but I guess we're going to talk about choosing this. So, I mean, it's good that it's universal in that sense. So let's make it plausible that this could, produce like non-trivial permutations. We're going to imagine choosing everything at random, though. Yeah. So here, if the depth is d, then the size is, like pretty much exactly d times n over 3. And that means the key size is just, you don't have this extra log factor, it's just d times n. Another thing is that, well, chips are usually in 2D in this world. And there's some reasons, as we'll see later, that you might prefer to have like a 2D kind of brickwork architecture. Here's my bad PowerPoint drawing skills. So these are like maybe a square root n by square root n of grid of bits. And these are like the wires coming out. And then you maybe put in like layers of these permutation gates, where one thing you can do is like, do kind of this like 1D local brickwork stuff on the columns, and then like have a layer where you do those 1D brickwork stuff on the rows, and then like stack some of these together. And this would be some kind of like 2D brickwork. Okay, so for all these slightly different formats, you could ask like, okay, is Gauer's conjecture true? Like, we just pick all the gates at random now. Like, is this cryptographically secure pseudorandom permutation family? How big should these circuits be in order to hopefully make this true? And how, what is the hope for exponentially small advantage, which the adversary has in telling the difference between a random reversible circuit and a truly random permutation? And what would you even like count as evidence? I guess we don't hope to prove anything like completely as a random permutation. So what things can you do if you like hope to advocate that like maybe Gauer's conjecture is true, that this is cryptographically pseudorandom? Okay, so one thing that you can try to do, and this is what people seem to have done a fair amount, is to, instead of look at cryptographic pseudorandomness, like come up with some notion of like statistical pseudorandomness that you can actually prove things about. So it brings us to this definition of this almost k-wise independence. So basically the idea here is like, imagine a slightly different model of security where the adversary can only see like k, that's a parameter. You put output pairs as a permutation, and then you try to prove statistical security even against an unbounded time adversary. Maybe more formally, here's the definition of what it would mean for like a probability distribution on pi, like random 1D local reversible circuits with n cubed gates or something, to be almost k-wise independent. So just let D be the set of all k tuples of n-bit strings, and then your probability distribution on permutations pi is epsilon almost k-wise independent if for every like worst case starting tuple of k n-bit strings, you pick like a random permutation from your pseudorandom family, like the random reversible circuits, apply it to each of these k distinct strings. Well, if I were a truly random permutation, then what you would get out would just be like uniform distribution on all the k tuples of distinct strings. And you're hoping that the total variation distance between that truly uniform distribution and what you actually see is very small, smaller than some epsilon. Okay, and maybe in this talk, epsilon, there's a lot of parameters, so I'll have a default value for epsilon that we'll sometimes use. The default value is like 2 to minus kn. So like the size of D is basically 2 to the kn. So like if epsilon is smaller than even 1 over that, that would be a really excellent value of epsilon. Any questions about this definition?
Just one question. If you replace the permutation, say, by a random linear permutation, then obviously you can still hope to get the statistical K was independent. Oh, I guess not. Probably not. It's a linear function.
Yeah.
But for linearly independent inputs, you can still hope to get
Yeah, that, I don't know anything about that, but yeah, you might.
So you can first map X to an error corrected, like, with the code, and then apply it.
sometimes some non-people know K was
Yeah, I think about that, but we're thinking about. Okay, so I'm going to show you, or tell you various results about how different kinds of random reversible circuits are K-wise independent for some parameters. And you might say, well, this is interesting. For example, is this evidence for cryptographic security? Well, it's up to your taste, but okay, here's some reasons why you might care to do this. At least you prove something. We got to prove something in our work. I guess like two-wise independence provides security against some like basic cryptographic attacks like linear attacks, differential attacks. Also, like maybe you care about things other than cryptography, and in fact, these constructions have non-cryptographic uses. Sometimes in like, for example, the field of de-randomization, like this is the exact thing you want. You want like almost K-wise independent permutations for some purposes, like, for example, constructing explicit near-Ramanujan graphs. And then finally, there exists this conjecture made by Uri, Magen, Myers, and Rakoff, who are studying this stuff, that perhaps if you have a distribution on permutations that's almost four-wise independent, then it's cryptographically secure. I think this is considered like very optimistic conjecture. But I guess, they write in their paper, it has the feature that it's like falsifiable. So that's good at least. And then 20 years, nobody's falsified it. So.
This is the difference between you and us.
Yeah.
But we call it tree.
So you can have these three quantities with crazy like random rational functions over a finite field gives you three, and this is broken. And I guess this was the reason.
Well, this is the reason why it's just 4 here.
Yeah. But then since then we have a lot of other ways of building. We're not known at the time building almost K-wise independent permutations. So maybe the conjecture was missing from relative to what we know today.
Yeah, maybe. Yeah. Well, I'm not saying I believe this conjecture. But for example, I think like it's not known how to get explicit exactly four-wise independent permutations.
Perfectly.
Yeah. But of course, yeah, perfect is asking too much. Okay. Well, anyway, at least you proved something.
Are there results by Shachar Lobet and others that perfect it's like existential?
Yeah, Alon and Shachar have some papers on this. Okay, so I'll tell you some such results. So this is the first result that was on about this topic by Gowers. And okay, you showed assuming some like conditions, like it's more precise than this, but here's the summary. K is bigger than n cubed and some like other funny conditions on n full. And if you pick a random reversible n-bit circuit with like k cubed, n cubed gates, throughout this talk, twiddle hides polynomial factors or polylog factors. Then it's almost K-wise independent. And here when I drop the epsilon, I mean with this default parameter of 2 to the minus n times k. Yeah, so it's pretty good. If you believe this four-wise conjecture, you can set k to be 4 and then hope that like with n cubed random gates, maybe it's cryptographically secure. You can still hope that even if you don't believe it. Okay, now I'll just tell you a bunch more results like this. Oh, I guess first I'll mention like, okay, how does he do it in a nutshell, or like how do you prove results like this? It's kind of like spectral methods and like random walk methods. So order to understand what you're trying to do, like imagine this thing is almost like a Cayley graph, but I guess the real name is Schreier graph, where like you build a graph where the vertex set is like all the k tuples of n-bit strings, and you look at this like set of all like single gates. Like if you look at all single gates, of which there are at 8 factorial times n minus 1 times n minus 2 of them, that choose 3 wires in a 1-8-1 permutation. We call this like a generating set, so a subset of all permutations of n-bit strings. And in this Schreier graph, the edges are labeled by the generating set, like saying like, oh, if I do this gate, well, how will this k tuple of n-bit strings change? And now, like a reversible circuit of size s is really just like a list of like s many generators. So it's like a walk in this graph of length s. And really what you want to show is that like for any starting point in this big graph with 2 to the kn vertices, you take a random walk of length s, then you're, close to mixed. You're close in TV distance to being uniformly distributed. And, the most naive way to bound this total variation mixing time is like kn, that's like the log of the number of vertices, times the reciprocal of the spectral gap for this random walk. And so Gowers was like, okay, I just have to show the spectral gap for this particular random walk is not too small. And okay, you showed that up to log factors, it's at least 1 over k squared n squared. And there are many different methods you can try to use to analyze fast mixing of random walks. And one is canonical paths, and this is the technique you use. So it's, yeah. Okay, so then other people made some improvements. So this particular paper, Guggenhagen, Myers, Rakoff, basically got rid of like all these like minor conditions here. So it worked for every k and every n, this same bound. And there's a very great paper by Brodsky and Hori where they improved the gap to show that it's larger, like 1 over k times n squared. And using comparison method like coupling and some ideas from reversible computation, field studied by physicists. And in particular, that means that you take still n cubed, but like times k squared many random gates. This suffices for almost ky is independent. Okay, yeah, and then like me and William thought about this recently, and we improved the gap to 1 over k times n. We got like rid of 1 factor of n, and this is even for like 1D local gates, so gates that operate on consecutive wires. And yeah, that's nice because then it shows that something like n squared random reversible 1D local gates suffice for almost ky. Oh wait, there's more. Like people really seem to get into working on this problem in 2024. Actually, one additional thing we did, if you remember, this is like the picture for like 1D local gates, and then there was this picture for like brickwork architecture. And we also showed that the spectral gap, where if in one step of your random walk you put down like 1 big layer of gates, then you might hope that we get rid of the factor of n in the gap, and we show that it does. So the gap is like 1 over k, or like 1 layer of brickwork gates. And therefore, the random reversible brickwork circuits of depth linear in n, so still n squared gates, but like this has this nice layout. It's like linear in n depth, and the quadratic dependence on k also suffice for almost ky's independent permutation. Okay, so I don't know if you believe this crazy conjecture, then a circuit that looks like this with depth and width n could be cryptographically secure. Okay, I'm not going to get into too much, but there's a reason I'm putting some details of how we did it on this slide. So first of all, to just get rid of the first factor of n, we used an interesting induction on n strategy from this paper by Hopperkamp, Hunter, Jones. And since this problem is about like, you've got a lot of Boolean strings, you might hope that analysis of Boolean functions is relevant. We use some analysis of Boolean functions to work on the case when n is large, and then you can combine this with the results of Brodsky and Hori for when n is small compared to k. And then if you want to get the similar result but with these like 1D local gates, then you need the more sophisticated induction on n strategy that we borrowed from this paper. These guys used the result of this guy from 1996. And then if you want the brickwork case, we had to also, as another ingredient, use the so-called detectability lemma from this paper by Aharonov et al. And actually, the main reason I put up all these details, even though I'm not going to get into them, is this funny fact that like all these yellow people are physicists. So like almost all the tools we use, maybe except for Brodsky and Horry, from these physics papers, which is funny. And later I'll say a few words about why physicists are also interested in these kinds of questions.
Connection between spectral gap and mixing time types. Could you have a small spectral gap and
I'm glad you asked that question, and I'm glad like William asked that question as well. I'll tell you about what he'll tell us about it just now.
Sometimes they try to validate the conjectures experimentally before trying to prove them. So is this being done also in this context? Or can the hope to?
Well, it's a good question, although I don't really know how to like validate. I thought about this, validate anything about this. There's no trouble to like make a random circuit.
small and
Yeah, huge. I mean, it's even like tried to check, yeah, that like it's close to 2i's independent or something, like 2 to the n factorial is very big. So yeah,
so small and right?
yeah, I guess.
Oh,
Yeah, I mean, yeah,
very small.
very, very small n, like n equals. Yeah.
Not only select the physicists who they have their heuristic way
Yeah.
of thinking.
Yeah, I would love to like get some kind of.
At least guessing where the line between true and false is based on some heuristic independence.
Yeah, you know, like Ron Kennedy like works on this stuff a lot, and I think he's like talking to physicists about trying to get their intuitions on stuff, but I don't understand that. So that's a good question. Let me briefly say something about shortening the key before I go on to back to the main topic. This is like the subject of de-randomization. So you can ask kind of this side question of like, oh, how many random bits do you need to generate like a random circuit that is maybe approximately KY's independent? Oh, I used the wrong term here, K design. It's the same thing. So what I told you before is like, okay, I mean, if you make a random circuit with like S gates, then, you know, that takes S times log n random bits. But actually, you know, there's all sorts of work in computer science literature on de-randomization. There's like lots of de-randomization technology. And coming out of this, like actually SL equals L stuff, there's this de-randomized squaring work. And yeah, way back when Kaplan, Knorr, and Reingold showed that actually to get this approximate KY's independence results, you don't actually have to pick the S gates totally at random. You can pick them in like a pseudo-random fashion. And in a way that like only uses like this many random bits, basically K times n, which is really like the minimum amount of like random bits you could hope to use. So like maybe your circuits, you know, depending on which results you're using, might have like n squared, k squared, or n cubed, k cubed gates, but you only really need kn random bits to pick them. So this would be like the key length. So Kaplan, Knorr, and Reingold got this kind of result using de-randomization technology. Actually, this group theorist, Martin Kasavov, gave us the same result, but in a totally different way. I bring this up because I'll mention his name once later. He gave like a constant size generating set for the Cayley graph on the symmetric group, which makes it into like an expander with like constant spectral gap. And if you know this constant size generating set, this is not like, you know, like little 3-bit gates, but like its generators would be more like, well, it's hard to say because it's a complicated paper, but like each generator might be like a size n or maybe size n squared, let's say size n circuit. But then he shows that if you just plunk down one of these, you know, 10 different circuits, that has like a constant spectral gap. And so then you can get this result by taking a walk of length, just k times n.
so a priori, these permutations, these generators could be very hard to compute
Yeah.
as permutations, but
Yeah, so it's if you read his paper, it's like really hard to tell if they're hard to compute or easy to compute or what. There's like a more recent paper from like 2020 with Praise where they make it much more explicit, and some people have looked at his paper and shown that these generating sets, they have circuit complexity, I think order n. I'm not totally sure of the details because you also want them to be like done with reversible circuits. I think maybe I didn't read the details, but maybe like recently people have even shown that these Kasabov generators can be done with like order n size. So yeah, the question here is about what is the circuit complexity of this generator?
So this is shuffling cards. There you need total randomness is limited, but limited randomness is not useful in the problem because there's been a lot of literature on different card shuffling.
Yeah, the card shuffling literature is, I always get confused about this, but I think it's like mostly distinct in the sense that like you're really interested in like the circuit complexity. I mean, it can be related, but like really operating on like the names of the elements, that's like bit string, as opposed to like just the cards. So maybe some of these Thorpe shuffles do like involve understanding they like operate on like the bit names of the cards, but I haven't found like too much connection between like this stuff and others. Like somehow all this stuff became a very popular topic in 2000, well, recently. And this is what William and I proved. I mean, we proved it in 2023. And then, for example, this gang, yeah, gave like incomparable, a pretty cool result where they showed that the gap for a random gate, not a 1D local gate, but a random gate, is 1/n without this k factor. And that means you get rid of one factor of k here and show that like k times n squared random reversible gate suffice for almost ky is independent. And somehow this used like, I actually didn't fully read it, but like somehow it uses the Kasabov result in some way. And some of these people are physicists, and physics people are really obsessed with like getting linear dependence on k. I don't know. I always care about the parameter called n more than one called k. There's reasons to care about the k as well. William and Lucas Greta and Los Palacanos addressed your question. They were like, you know, with this modern world, we have smarter methods to like analyze mixing time than like spectral methods. And so they founded the log subload constant for this chain. And for example, they can deduce this result, which is much better if you're not trying to get like an amazing epsilon, which, you know, for cryptography purposes, like you don't have to like try to get epsilon being this default value of 2 to minus kn. So they actually showed that like k times n, a random reversible gate suffice. If you want to get epsilon almost ky is independent, apply a logarithmic dependence on 1/epsilon. So if you decide, oh, I really do want epsilon to be like 2 to the minus nk, then okay, you pick up another n times k factor. But if you just want like, I don't know, epsilon to be 1/n to the log n, then you only pick up like a polylog factor here. And so like maybe, yes.
First result is not parameterized by epsilon, is that right?
Oh, here,
Here,
epsilon is just fixed to be 2 to the minus kn. We can't achieve anything else. This one, they do have epsilon in their parameters, but I didn't write it. I think they get, and they get like this plus n times k times log 1/epsilon. So I guess they get like this plus this, if I'm not mistaken. Okay, so this might even make you believe that random circuits with order n gates or twiddle n gates could be cryptographically secure. But they're not done. These three guys sitting here, William and Will and Nicholas, they looked at this 2D brick architecture, and show that, for example, with depth root n, you get kind of a similar result. You get like epsilon almost k-wise independence, where epsilon is, okay, not 2 to the minus kn, but it's still like really small. It's like 2 to the minus root n. And what's also interesting about it is like somehow they did it only using spectral methods. Maybe not in the simplest way, but like only using spectral methods. So I'm trying to still get the vibe on like why and when, you know, log Sobolev helps, or like some smarter spectral methods help, or what. In fact, as you might guess, like, okay, if you can build 3-dimensional brickwork circuits, you can get the depth down to like n to the 1/3. And in fact, for any capital D that goes up to around log n, they show that like n to the 1/d depth circuits suffices with error that's like 2 to the minus n to the 1/d. You're ignoring the dependence on k. And you can take d almost all the way up to log n, which means that you can get this down to like close to poly log n, or n to the low of 1, and thereby again get like size that's basically nearly linear in n, but it has this, you know, additional nice geometric structure and tau. Okay, so in the last 5 minutes, I'll just tell you a couple of thoughts about quantum and crypto. So why actually were the physicists interested so much? Well, reversible gates are also quantum gates, and then if you just like also say, oh, I'm going to throw in random Hadamard gates as well, then you get random quantum circuits, and you get to the question of like, are all these like almost k-wise independent unitaries? And one reason to care is that, like in quantum algorithms, they sometimes really wish they could apply a completely random unitary to their quantum states, but this is very algorithmically expensive, so they actually want efficient compute pseudo-random unitaries. Also, the subject of like cryptographically secure pseudo-random unitaries and pseudo-random states, sort of concepts introduced in this very awesome paper by Qi Liu and Song. It's a really interesting area. I don't know so much about it, but like it's known that like if you have such cryptographically secure quantum objects, you can on one hand build a lot of interesting cryptography from them. On the other hand, like this work by Kretschmer show that there are like oracle worlds relative to which cryptographically secure quantum stuff exists, even though P equals NP. So like even though you're in Algorithmica, you still have quantum, or you still have crypto thanks, there's some crypto thanks to quantum cryptographic primitives. So that's pretty cool. I mean, even though P does not equal NP, it's interesting to think about. Finally, random quantum circuits are a very serious model for black holes, apparently. This interest maybe in this paper by Hayden and Preskill. In fact, in this Hayden Preskill paper, they even start by saying like, our toy model for black holes will be random reversible circuits, just like we talked about in this talk. They're like, okay, we got to get serious and make them random quantum circuits. And for example, they really want to know, and I guess we more or less do now know, if you make a random quantum circuit just by throwing down S quantum gates, does the resulting unitary actually have complexity comparable to S? Which is probably, you can ask yourself, what is the smallest quantum circuit that computes the same unitary that this random one I just picked does? Or like maybe approximately.
Like counting arguments?
You would think like, okay, in the classical world, where everything is discrete, you would think that like a counting argument would help you answer this question. It's actually not so easy. I'll say something about the classical world in a second. Yeah, because it's also because like the complexity corresponds to the area of the black hole or something. So they really want to know there's like time grows. Yeah, I don't understand. And this is actually why they're really interested in the K parameter. They want to show that like, you know, somehow the complexity is maybe you could also map onto like the K for which the thing is K-wise, approximately K-wise independent. Does this grow linearly as you like in K when you add more K? Okay, so finally I'll just end with some cryptographic questions that one might still think about. Obviously, the first one is Gauss's conjecture true? our random reversible circuits of size n squared, maybe even order nearly linear size, cryptographically secure, and it's such a nice candidate. Like, it'd be nice if it were believed to be true. So what maybe would count as evidence is a good question.
Does it immediately imply the epsilon biasness? Maybe, right? The KOS independence with like tiny.
What do you mean epsilon bias?
You can compute linear functions on the entire truth
Linear
table.
function can,
I don't know. Well, if it's true, it would be good for anything. I mean, after all, one-way functions exist. We have secure PRPs anyway. I don't know, maybe like Ron Kennedy and some other people have this cool paper, which I also admit I haven't read yet in detail. But yeah, where you assume Gowers conjecture and some other speculative conjecture, then maybe you can get the general purpose obfuscation.
Gauss conjecture is a conservative part.
There's a problem, Mr. CSP. This is the minimum reversible circuit size problem, which Gowers also asked about like 10 years ago. Actually, William and I proved a little something about this, although just a little something. If one-way functions exist, then there's no deterministic algorithm that can distinguish a random n-bit permutation in an oracle from one computable by like an n-cube size reversible circuit. And the real question here, though, is it should still be true that an adversary that can see literally the whole truth table of an n-bit permutation and can run in 2 to the order n time still probably shouldn't be able to tell if this permutation is computable by like a very small reversible circuit or not. So that's an interesting question to try to think about. Yeah, then there's this compressibility question. So let's say you pick a random reversible circuit with S gates, but then you ask yourself, well, is it possible that the permutation it computes is actually computable by a much smaller reversible circuit? Every instinct is like, no, definitely not. It's not so easy to like solve this with like a counting argument. In fact, it's not until like these very recent papers by like William and this other group that prove something like this. They prove that it's with high probability at least S over n cubed. Probably its complexity should be like S minus S over n cubed. So it's a start, but like it's a little bit surprising that like it's hard to prove a lot about this. And then one other question I know about, so that some people have thought about, is the question of universal PRPs. So maybe you can show that PRPs exist if and only if random poly-size reversible circuits are PRPs. I think there's some hope that maybe you could try to solve it. And that's it. Thank you. I got office hours, so I gotta go. So,